So I'm Adda Athanasopoulos-Zekkos from UC Berkeley, and I've been looking at, studying, investigating levees for the better part of the last 20 years since starting my PhD. So today we're going to get a little bit up close and personal with them and try and better understand flood protection, the role levees play, and then hopefully look a little bit into the future on things that we can do, things that are evolving right now to improve certain things. So let's start first by looking at some, okay, is it advancing? Okay. So let's look at some failures. We have all seen these types of videos and images in the news. Unfortunately, these are all different types of levee failures that have just occurred in the last few years. There have been, of course, many, countless similar types of failures that have very negative consequences for people and for critical infrastructure. Between the years of 1983 and 2023, NOAA basically gives an estimate per state on the dollar, basically, cost of these types of events. And as we see, it's in the order of tens, if not hundreds of billions between the different states. So this is a very important and critical issue that should not be overlooked. We have levees in many different places. I'm just showing the US, but that is of course true around the world as well. So I always feel that they're a little bit misunderstood and maybe not given the spotlight that, say, dams get or a critical pipeline. And yet they play such a significant role in flood defense, in reducing flood risk for so many communities. So let's kind of interview them a little bit and get some facts about them. So just the National Levee Database that was introduced in less than 10 years ago has already documented about 30,000 miles of levees. That is enough to bring you one time, if not a little bit more, around the Earth. And that does not include the thousands of levees that are still out there that are still not documented because of ownership issues. About 17 million people either live or work in places whose risk is being reduced by the presence of these systems. And about $2 trillion property is also protected by these levees. In a recent report that was published by ASCE, 4,000 of these levees, 4,000 miles of these levees were characterized as high to moderate high risk of failure. And I think the number that's even more daunting is the fact that about 80% of those levees were deemed to possibly fail sometime in the future before being overtopped. So there are multiple critical failure mechanisms involved here. And as I mentioned before, what's really interesting about these systems is that you really have to use Google Earth to really appreciate their extent. So we're going to take a very quick little trip, and all we're going to see is about a 0.006% of the kind of system we are typically called to evaluate and assess. And the other important thing that we see that again separates these types of systems like levees from, as I mentioned, other critical infrastructure like a pipeline that we heard earlier today in the panel, or dams and other type of infrastructure, is that they are extremely spatially distributed. They interact and sometimes interrupt other type of critical infrastructure. And I think the most important perhaps is that they're not owned by the same entity. And this brings a lot of challenges that we typically don't have to deal with when it comes to other systems. So a few more facts to see what the Army Corps of Engineers has projected in an ideal world where we all win the lottery, right, and we all give our pool funds to the Army Corps of Engineers. They would need about $21 billion to support the current system. Okay, this is not about introducing new aspects to the system, just making sure the current one works the way it's supposed to. As I mentioned, there was a national levee safety program that tried to mirror the similar dam program. It was established, again, about 10 years ago. There was a decision to appropriate about $79 million annually to the levees. And just to give you a reference, in 2021, they only received 5 million of those. And so this is how different the numbers are between what it is that we're able to provide and what is really needed to maintain these systems and keep them up. And I haven't even mentioned the two little words that our panel so brilliantly discussed, climate change. This is not the money that we need to actually bring it to where we think we're going to be in 2050, 2060, 2100. Another really big bottleneck when it comes to levies is that there are no guidelines, no official guidelines. If you open up your cell phones now and you try to look, how should I do this, something that has been decided on by panels, agreed upon, you're not going to find anything. There's going to be advice, there's going to be documentation of best practices, for example, but there's no unified national standard, which I think combined with the different ownership of different segments of the system creates a huge problem. And then finally, we must also not forget that, as I mentioned at the beginning, these levees are there to reduce flood risk. In some areas, they will never really eliminated the same way that we build other infrastructure in civil engineering. And so we always need to think that what comes next? So let's say in the event that we do have an overtopping, we do have a failure, are there mechanisms in place that will allow us to, say, evacuate a certain community, open up these types of routes, assess these types of impacts in the post-disaster era? And of course, as geotechnical engineers, we're very, very familiar with uncertainties. And this is a problem that just has uncertainty from start to end. There is uncertainty in the loading situation, the hazards. We were just talking about earlier today about what do you incorporate? Is it the 100-year flood? Is it the 500-year flood? Is it the 1,000-year flood? I was in a panel for earthquakes. They're talking about the 10,000-year return period event. Are we going to start doing similar things with levees, given what it is that is at stake here? And then you go to performance. And for some of these systems, we don't know where they are. And for those that we do know, sometimes we don't know what's under them. And even for sometimes that we do know what's under them, we're not allowed to walk them because they're privately owned. And so there's just so much uncertainty in characterizing the system in the first place. And if that was not bad enough, then we're not even sure about what it is that the consequences are going to be, because we haven't really documented what a flood from a certain point would mean, right? What is the cascading effect? Is it blocking out a community from being able to evacuate? Is it blocking their way to reach a hospital? How many schools are going to be out of session for months on end following a flood? All these things are important to keep in mind. And again, there's so much uncertainty everywhere. And so, of course, like Carlos, I'm also an optimist, and so I like to think that there's many things that we can do. And this is what we've been trying to do. And again, we have to keep in mind something important that I think all of geotechnical engineers are familiar with. Whenever we're looking at infrastructure, we always know that there's more than one way that things can go wrong. And as I tell my students in class, the unfortunate thing for us is that nature already has the answer sheet. Nature will know what to do and how to do it. So it's really up to us to figure it out in time so we can get there first. Especially with levees, we can have all sorts of things happening under seepage, through seepage, overtopping. Animals can interact and create holes in them without us realizing until it's too late. We can have so many different things. As I mentioned, the interaction with other type of infrastructure that creates these transition points. That was one of the first things that we noticed in 2005 after Hurricane Katrina, for example, in Louisiana. A lot of the failures happened at these transition points where a railroad has to cross a levee, or where my levee as owner A interacts with your levee as owner B, and none of us can decide who's really in charge for how to make that connection work. And so there's all the governance issue on top of the engineering issues that we need to deal with. And we also need to do that in time, right? So I know 3D is very difficult. Brady was talking about it yesterday. How do we bring a 3D in site response, which is, I think, amazing. We want to do the same thing for these systems, but you also need to add the concept of time, because these are changing systems. Things are happening all the time, and perhaps what you see today is not going to be the same next year, or just following a seasonal change. And so we've been looking at trying to leverage as much of the technology and the means that we have available. I am a very big believer that I'm willing to try anything as long as it brings more information for me to better complete the puzzle, which is what we do as geotechnical engineers. So we can start with characterizing the subsurface of levees, and we can do that using traditional characterization tools. I'll call them traditional compared to some else, like the cone penetration test that we can perform in very specific locations. And so what this provides me is information, but at that specific location, right? And this is what we're going to see a little bit of a theme in the next few slides, how different types of information will come at different locations, and then I'm going to have to be able to stitch that all together. And so I have these unique CPT profiles. Of course, this is an ideal world where for this section of levee, I have 2 CPTs. I've had to deal with these systems, and I've had to go for miles before encountering information from one CPT, and so talk about extrapolating. And I think that that's where geophysical approaches can become extremely helpful. They can cover more ground. They can bring in this 2-dimensional approach. Unfortunately, we don't have Thor always banging the hammer for us, but we try to make it work. And then you can introduce this pulse under the ground that will sample the subsurface materials, and then it'll basically come up through an inversion method with some type of 2-dimensional shear wave velocity profile, for example. And we can not just stop at shear wave velocity, we can also look at electrical resistivity, as we're going to see later on. But the point here is that now I'm getting a little bit more of a 2-dimensional, and then I can use the CPTs in the specific locations, right, and just start building and bringing everything together. Of course, we mustn't forget about the surface structure of the levee. It's very important for me to understand what the crest is doing versus the toe. Is there cracking? Is there any kind of subsidence? And so, of course, we have a lot of tools to be able to do that. So remote sensing, for one, of course, we have satellites that we can leverage. There's different level of accuracies there, but we can use them as a first scan. You can use drones to come in closer, get even better resolution for some sections. You can do that below water, of course. We can use SPOT, for example, that we have at Berkeley to help us reach some sections that maybe we can't. Some of these levees are just extremely vegetated, and so this can come in handy. And you can use other types of surface sensors, like fiber optic sensors. Again, the point is that everything needs to come together so that you can look at information like this. And so this is beyond the cartoon schematic. This is some real data from a section in the levee. So this could be your RGB imagery. You can connect that with thermal. You can connect that then with LiDAR, and it can all come together. And this is work by Brittany Russo, and she's going to be talking about that later this morning. And you can then start to bring things together and then compare them between different seasons, between different years, because for some of these techniques, it's not really the absolute value that's important, it's really the difference, right? So is there something changing in the system that will then flag it for you so that you can see why is it changing? Kenichi Soga and his group have done some great work with fiber optics, and they have been able basically to really capture the difference in the water table with strains in the fiber optics and essentially monitoring the heartbeat of the levee. And when we can bring this all together, the LiDAR, the optical, the thermal, subsurface information, we can basically fuse all that, and it can give us the problematic sections. And this information will allow us to then color sections red, orange, green, and then we can combine that with population data, land use data, very important to bring in the consequences for these systems so that you can also understand a failure, what are the implications, what kind of areas does it affect. And in closing, I want to also discuss a new paradigm shift that we're proposing for looking at risk for flood protection. It has been for a long time a very static thing. We had flood risk maps, for example. You go and you find your site, and we really want to see the risk as a process. What created it and what processes can basically either increase it or decrease it. And this is work that we're doing with Anna Sarah Lobet at Berkeley. And this is going to help us incorporate equity, climate adaptation, and environmental sustainability in a much better way than we're doing right now. So with that, I would like to thank you for your attention.